Hey love, you alright? Yeah, not too bad. Just working on a video at the moment. Yeah, just doing one on Pat and Nat. No, not Pat and Nat down the road. Well, no, I know I didn't get invited, but it doesn't mean I'm going to make a video about them. No, not Pat and Nat. I'm doing it about another Pat and Nat. Oh, alright, okay. Right, I'll see you in a bit then, bye. Network address translation and its extension port address translation are used in most networks around the world. I say most because of the rise of IPv6, which doesn't require any sort of NAT. So let's go through and explain what NAT and PAT are. Before we go in depth on network address translation and port address translation, we need to understand what an IP address is. An IP address is a unique logical address to identify a device on a local or public network. When a device sends data, it places the source and the destination IP address, as well as other data, into a packet and fires it off to the destination, whether that's on the local area network or the wide area network, in other words, out on the internet. There is a little bit more to this, but to understand it, we need to go back in time when IPv4 was first created. When IPv4 was created back in the 1980s, there were over 4 billion unique addresses. Back then, there wasn't as many users of what we call the internet now, so over 4 billion addresses were not seen really as an issue. Every host would have obtained a unique IP address, and it was even theorised that the internet would never take off and it was just a fad. A bit like TikTok, hopefully. But pretty quickly, technology and communication grew, as did the population of the planet, which in today's times stands at over 7 billion people. More and more people became connected using the internet, households using multiple devices such as phones, laptops and tablets, and businesses solely relying on the internet to operate day to day. And these public IPv4 addresses rapidly depleted and became exhausted, which needed to be addressed. So what is IPv4, public IP addresses and private IP addresses, and why have they become exhausted? Well, let's start with the private and reserved addresses. If you were to look on your phone or laptop right now, while connected to your local area network, your device IP will most likely start with 192.168. There are other addresses as well, such as 172.16, 17.18 through to 31, or 10.x.x.x. These are private addresses and are used internally, meaning they will only be used on devices inside your private network, such as your mobile devices, computers, laptops and games consoles and so on. When you connect your phone, laptop or any device to your Wi-Fi Ethernet, you're on the private local area network. If you try to route a private address out to the public internet, the packets would just get dropped, as millions of homes will be using the same private addressing space. Even the houses on your street will most likely be using 192.168 internally. Then we have public addressing. These are the addresses assigned by the ISP to your router to allow the private networks to connect to the internet and access external resources. And these addresses are routable across the internet. Everything on the internet requires an IP address. These public addresses also have ranges. A Class A public range is from 1.0.0.0 to 127.0.0.0. Of course, the 10.0.0.0 to 10.255.255 and 255 range is reserved for private addressing. The Class B public range is 128.0.0.0 to 191.255.0.0 and 172.16.0.0 through to 172.31.255.255 is reserved for private IP addressing. And the Class C public range is 192.0.0.0 to 223.255.255.0 with 192.168.0.0 through to 192.168.255.255 reserved for private IP addressing. Then we've got some special addressing. We have a loopback address which uses 127.0.0.1 to 127.255.255.255, which is used for network testing. APIPA, or the automatic private IP addressing, uses 169.254.0.0 to 169.254.255.255, which is the self-assigned IP address should your host not have access to a DHCP server. Multicast uses 224.0.0.0 to 239.255.255.255, and then there's research, which uses 240.0.0.0 to 255.255.255.255. So the ISP, or the Internet Service Provider, gets a block of IP addresses allocated to them from the IANA, the Internet Assigned Numbers Authority. An example, such as Sky, who is a very popular ISP in the UK, have many IPv4 blocks of addresses, but one range here is giving them a block size of 2,097,152 IP addresses to allocate to their customers. 2 million seems a lot, but there's 67 million people in the UK. Say each house has a public IP address, that 2 million is going to go very soon. And then some homes and businesses have multiple public IP address blocks assigned to them. My house, however, has one public IP, so say that was 1.34.234.14, but someone else could have multiple public addresses, say a block of 5.65.33.230 through to 5.65.33.232. They'd have 3 public addresses assigned to that location from their ISP. Again, these IPv4 addresses will get used up very quickly. So this takes me on to NAT, which is used to extend the life of IPv4. So we need to do some translation, which is what NAT does, and I'll go through a few NAT types. We have static NAT, dynamic NAT, static PAT, and dynamic PAT. PAT being the port address translation. This is also known as overload. NAT converts the private IPv4 address to a public address to make the IP packet routable over the internet to its destination, which would be another public IP address. It operates at layer 3 of the OSI model, the network link layer, which is where IP lives. Routers can do NAT, but so can other devices such as load balancers and even some servers. So let's start with dynamic NAT. Dynamic NAT is mainly used in situations where you had a pool of public IP addresses assigned from the ISP, and the internal hosts can dynamically use whichever public IP address is free. So as an example, you've got 3 public IP addresses assigned from the ISP, 11.22.33.44, 11.22.33.45, 11.22.33.46. And you have 3 host devices on the local area network. Host 1 using 192.168.1.200, host 2 using 192.168.1.201, and host 3 using 192.168.1.202. Host 1 requests a web page, so the IP packet header will contain the source IP address, 192.168.1.200. And the destination address is something on the public internet. Let's say it's 99.88.77.66. When the packet's sent to the router, it will see that it's destined for the internet, so it will take the source IP and put that in a NAT translation table, and the packet will be then translated. The source address will change from the private IP address to one of the available public IP addresses. Let's say it's 11.22.33.44, and that address will also be put in the translation table. Then the packet is sent off to its destination, so 99.88.77.66. And when the response comes back, the destination will be the original source, so 11.22.33.44. It hits the router, which checks the translation table and changes the public IP back to a private IP and sends the information onto the host device. This will be the same for host 2 and host 3, but if public address 1 is in use, they will dynamically use the other 2 free public addresses as part of their translation from LAN to WAN. But what if a 4th private host wants to connect? It's got a private address of 192.168.1.203. It sends its packet to the router, but the 3 public addresses are in use, so the packet is going to be dropped. You can't use the same public IP address for multiple devices using dynamic NAT. If a host stops using one of the 3 public addresses, host 4 can now get out to the internet. but that will affect host 1 when it wants to get out to the internet again. Notice as well how the ports aren't affected when using NAT. That's because ports operate at layer 4, the transport layer, which is what I'll be coming to shortly. Then we've got static NAT. Static NAT, also known as one-to-one NAT, is used to make an internal host or resource accessible from the internet, as well as allow the internal host access to the internet, but it has to be manually defined by a network admin. So say you had a server on the network, you could purchase a public IP address from the ISP and have that device accessible just by typing in the public IP address. Let's say the public IP supplied from the ISP is 44.55.66.77. The router would have a predefined list in the translation table to say, when source address 192.168.1.100 wants to go out to the internet to the destination, as for an example 99.88.77.66, translate it to 44.55.66.77. If we were remote to that network and the static NAT was configured, we'd just be able to type in the public IP address of the server. The packet would have a source address, for example, as 99.88.77.66, and the destination would be the public IP of that private network. So 44.55.66.77. Then we can access the server, but you would need a separate public IP to achieve this. The downside of static NAT is the cost of purchasing public IP addresses. It can become pretty expensive, and also with the exhaustion of IPv4 could be quite difficult to do. Then we have the most common form of NAT, one that we use every day. Everyone connecting to the internet uses this, and this is PAT, Port Address Translation, which is an extension of NAT and allows multiple private hosts to use a single public IP address, whereas NAT uses the available public IP addresses. PAT is more suited to the standard home, where they will have multiple host devices requiring access to the internet, but only have a single IP, like your average household. PAT operates at layer 4 of the OSI and will translate the IP address and the port number of the private IP address. So let's do an example. My house has a single public IP address. Let's say that's 99.88.77.66. My internal network, so my private network, is on 192.168.1.0/24. I want to access a resource on the internet using my phone. My phone is on 192.168.1.100. So the source address in the IP packet will be 192.168.1.100 port 1122. The source host device will generate a random port number. It has over 65,000 ports to choose from, so I just picked 1122. In the destination field of the packet will be the resource address of what's on the public internet. So that could be 44.55.66.77 port 443. We can see that destination is using a well-known port of 443, which is HTTPS. This port won't change. When the packet hits the router from the host, the router will put the source IP address in the translation table and translate it to the public IP address. So the public IP address of 99.88.77.66. But it will also translate the port number. So 192.168.1.100 port 1122 will translate something like 99.88.77.66 port 8899. And the destination will remain 44.55.66.77 port 443. And off it goes. It gets the request, and upon the return, the IP packet will now have changed. The source will now be what was the destination. So the source will be 44.55.66.77 port 443. And the destination will be the original source, 99.88.77.66 port 8899. It hits the router on the external side and gets untranslated by the translation table, and 99.88.77.66 port 8899 becomes 192.168.1.100 port 1122 and forwarded to the destination, which is our private host. Now at the same time, my wife is also making a web request. Her device private IP address is 192.168.1.200. Her device will generate a random port number and create an IP packet which will have the source IP as 192.168.1.200 port 3344, for example. with the destination of 77, 66, 55, 44, port 80 being HTTP. When it gets to the router, it will then put the private address in the translation table and convert that to the public IP address of 99, 88, 77, 66, so the same as what I was using, but it will choose a different port number, something like 6677 for instance. And off it goes. Upon its return, the IP packet source address will be what was the destination, so the source will be 77, 66, 55, 44, port 80. And the destination will be the original source, 99.88.77.66, port 667. It hits the router externally and gets untranslated from 99.88.77.66, port 6677, back to 192.168.1.200, port 3344, and it's forwarded to the source device. Both of us are using the same public IP address. We're both getting our private IP addresses translated to the public IP address, but we're also going out on different ports, which is what makes PAT much better suited for networks containing multiple devices and use one public IP address. You might think, hang on, the source address generates a random port number. Why does that need to be translated as well? Well, never say never, but on the rare occasion, source devices could generate the same random port number. And if it wasn't translated by the router, upon its return, the IP packet would be dropped because the router will see two entries exactly the same in the translation table. So that's why the router regenerates a random port number. So let's show this as an example. I've got my Draytech 2862 router and my laptop is the only host device connected to the LAN. I've got a private IPv4 address of 192.168.1.10. If I log in and go to the diagnostic page, then the NAT session table, we can then see the requests this machine is making. The first column is my private IP address. The second column is the random port number my laptop is generating. The IP packet then hits the router and the port number is regenerated by the router. In Draytech, this is called a pseudo port. Then off it goes out to WAN 2 with the destination address. So we are using PAT as the IP address and the port number is being changed. Remember, PAT works layer 4, so it can translate IP addresses and port numbers. If I go to my browser and go to channel4.com, then refresh the list in the Draytech router, I can see I get a load of public IP addresses. So I'm going to generate a ping to channel4.com and I get the reply of 99.80.196.166. I'm going to look for that address in the NAT sessions table. And when I've found it, I'll copy it and paste it into my browser. And I instantly get redirected to channel4.com. This doesn't work all the time, however, you may get redirected quite a bit. A lot of websites use shared servers and load balancers, meaning they'll have multiple IP addresses associated with the web page, or some web pages block access if you're trying to connect via an IP address and not using the FQDN or the fully qualified domain name. You can still land up in the wrong page because you have not navigated to the appropriate path of the web URL from where it's being hosted. If I do an NS lookup or name server lookup of the public IP for channel 4, I can see that the website is being hosted by Amazon Web Services. If I now go to sky.com, refresh the table in the router, I'll then do a ping and I get an address of 90.216.128.5. If I go to that IP, I don't get to the Sky website, but an area associated with Sky. So this is teachers.sky.com, for instance. Anyway, this video isn't on web hosting or how a website works. We've seen NAT working in real time. Continuing with NAT, dynamic PAT does not allow outside connections on the public internet to initiate communication with internal private hosts. Here's why. If we were to make a request to the public IP of 99.88.77.66 on port 65,000, the packet would get to the router, which will look in the translation table and see that that port mapping does not exist, and it would drop the packet. This is where we can do a static PAT. Static PAT and static NAT allows outside external hosts to initiate connections to access the internal network. With static PAT, we explicitly tell the router that anything coming in from, say, port 65,000 using the public IP is to be translated and forwarded to the resource. An example being if you needed to access a web server, for instance. So I'm going to use a Windows machine I have, and I've enabled a web server on it. You'd put the port forward rule in the router, so something coming in on the public IP port, again using 65,000, would be directed to the internal address of 192.168.1.250 on port 80, for example. So I've connected my laptop, which is running a web server, to the network, and the local address of that laptop is 192.168.1.12. In my Draytech, I'll go to NAT and port redirection and go to index 1 and click enable. I'll give the service a name, I'll call it web server, and leave the protocol and WAN interface as is for this example. The public port I'm going to put as 65,000, and the source IP I'm going to leave as any. You might want to access resource from any external IP address. That's why I'll leave that as any. The private IP will be that of the web server, so 192.168.1.12, and the private port is 80. This is the port we can use to access the web server. So I'll go to my browser and I'll type in what's my IP and take note of my public IP address. What I'll do now is I'm going to tether my Mac to my phone, so I'll be on a completely different network. I'm going to then disconnect my Mac from my local area network, so I solely rely on being on the tethered connection. I'm going to open the browser and go to my public IP and port 65,000. And I've now accessed the web server. That is a static PAT. Obviously this carries some security concerns as you've now punched a hole in the network for external access. Most of the time now, to connect remotely to devices, a lot of people will just use a VPN or a cloud-based access via something like Oversea or Demots. But dynamic PAT is how you can access the internet from your multiple devices in your property, which is using a single public IP address. PAT is the best method to preserve the public IP address spaces, as it's only using the single public IP. But now making a dent in IP is IP version 6, which uses a 128-bit identifier in comparison to IPv4, which is 32 bits. IPv6 doesn't require NAT, as the address space on IPv6 has quite a few more addresses than IPv4. So if you imagine IPv4 has an address space of 4.2 billion addresses, whereas IPv6 has 340 trillion addresses. So we won't be running out anytime soon.